On the 23rd of July 2012, the Sun launched a massive cloud of superheated plasma into space. It moved fast, nearly 3,000 kilometers per second, and it crossed Earth's orbit. But Earth was no longer there. 9 days earlier, our planet had been sitting directly in its path. Think about that for a second. 9 days may be the only reason the modern world kept running. If that eruption had happened just a little earlier, it could have hit Earth head-on. Power grids may have gone down. Satellites could have failed. Communication systems might have stopped working. And this was not some distant object slowly drifting through space. It came from the Sun, millions of miles away, yet it had enough energy to threaten systems here on the ground. So how does something that far away shut down electricity? What happens when the power goes out across an entire region and does not come back the next morning? How long can a modern city keep going without working pumps, cell towers, hospitals, fuel stations, or food deliveries? We did not survive that day because we were ready. We survived because Earth happened to be 9 days ahead. That was not protection. That was luck. On the 1st of September 1859, Richard Carrington was doing what he did almost every clear morning. He was watching the Sunday. Carrington had built a private observatory on his property in England. He spent hours studying sunspots and carefully drawing what he saw. It was slow, patient work, nothing dramatic. Then something changed. As he traced a large group of dark sunspots, 2 bright white patches suddenly appeared inside them. They were not small reflections. They were not faint. They looked brighter than the surface of the Sun itself. Carrington pulled back from the telescope. For a moment, he thought something had gone wrong with the equipment. Maybe the lens had shifted. Maybe light had entered the room. But when he looked again, the bright patches were still there. They moved across the sunspot group and slowly began to fade. The whole thing lasted about 5 minutes. Carrington knew he was seeing something unusual, so he called for someone to come and witness it, but no one arrived in time. By the time another person reached the observatory, the strange light was gone. Only the normal sunspots remained. That could have ended the story. One man, one telescope, one unexplained flash. But Carrington was not the only person who saw it. At nearly the same time, another amateur astronomer named Richard Hodgson was observing the Sun from a different location near London. He reported seeing the same kind of bright flash. 2 men, 2 separate telescopes. The same event at the same time. Later that year, they published their observations together. The scientific community did not know what to make of it. Some experts suggested they had been fooled by a passing cloud. Others blamed a problem with the telescopes. At the time, bright white flares on the Sun were not something science believed should happen. Carrington could describe what he saw. He just could not explain it. And that was the real importance of that morning. Human beings had witnessed something on the Sun that their science was not yet ready to understand. About 18 hours later, the sky began to change. At first, people thought they were looking at an unusually bright aurora, but this was nothing like the soft green light normally seen near the poles. The sky turned red, then purple, then a deep crimson that looked almost like fire. The lights appeared across North America and Europe. They were seen in Australia, New Zealand, the Caribbean, Hawaii, Colombia, and Jamaica. Places that almost never saw auroras were suddenly glowing in the middle of the night, and the light was strong. In some areas, people could stand outside and read a newspaper without a lamp. Gold miners in the Rocky Mountains woke up around 1 in the morning and started making breakfast. They honestly thought the sun was coming up. Roosters began crowing hours before dawn. In cities, people poured into the streets and looked up. Some were amazed. Others were frightened. A few thought the world might be ending. From the ground, it must have looked beautiful. But beauty was not the real story. Auroras usually stay close to the northern and southern poles because Earth's magnetic field guides charged particles toward those regions. This time, the lights reached much farther south. That meant Earth's magnetic shield was under enormous pressure. It was being pushed, stretched, and distorted by something coming from the Sunday. So the red sky was not just a rare natural light show, it was a warning. The planet's magnetic field had been hit hard enough to bend almost all the way toward the equator. People were watching the atmosphere glow. What they could not see was the force behind it. And that force was already beginning to move through the wires below them. At the time, the telegraph was the fastest communication system in the world. It was the internet of the 1800s. Messages traveled through long copper wires stretched across cities, states, and entire countries. People trusted the system because it was simple. A battery sent current through the line. The machine received the signal. But on that night, the machine stopped following the rules. Telegraph equipment began heating up. Metal relays glowed red in the dark. Paper tape caught fire on desks. Smoke poured out of wooden cabinets before operators even understood where it was coming from. Some workers were shocked hard enough to be knocked back. Others burned their hands on the brass keys. The insulation around the wires gave off the smell of burnt resin. Receivers clicked on their own, sending signals even when no one was touching them. It was like the network had come alive. In Boston, one operator thought the battery was causing the problem, so he disconnected it. The line kept working. That should have been impossible. There was no battery connected, no local power source. Yet electricity was still moving through the wire. The operator in Boston and another operator in Portland, Maine, realized they could still communicate. For nearly 2 hours, they sent messages using only the current flowing naturally through the telegraph line. And the strange part was, the signal sometimes worked better without the batteries. That electricity was not coming from a power station. It was not coming from the telegraph equipment. It was being created by the changing magnetic field around the entire planet. The storm above Earth was pushing electrical current through the wires below. People could see the red sky. But the real danger was already inside the system they depended on. So what actually came out of the sun? It was not sunlight. It was not a simple burst of heat. It was a coronal mass ejection, or CME. In plain English, the sun threw a massive cloud of superheated plasma into space. That cloud was packed with charged particles, and it carried part of the sun's magnetic field with it. Think of it like a huge magnetic storm moving through space. Normally, a CME takes about 3 or 4 days to travel the distance between the sun and Earth. The one in 1859 made the trip in about 17 hours and 40 minutes. That was incredibly fast. The reason was unusual. 2 days earlier, a smaller eruption had already traveled along the same path. It pushed much of the solar wind and other material out of the way. It was almost like a snowplow clearing a highway before a speeding truck came through. So when the larger cloud erupted, there was far less resistance in front of it. It raced toward Earth almost without slowing down. Then it reached our planet. Earth has its own magnetic field. Most of the time, that field helps protect us by guiding harmful charged particles around the planet. But the magnetic field inside this solar cloud was pointing in the worst possible direction. Instead of sliding past Earth's magnetic shield, it connected with it. That connection pulled the shield open. Charged particles poured into the upper atmosphere. When they collided with gases high above Earth, they produced the bright red, purple, and crimson auroras people saw across the world. The lights were beautiful, but they were also proof that Earth's magnetic defenses had been hit hard. What looked like a glowing sky was really the visible edge of a much larger magnetic storm. So how did a storm in space create electricity on the ground? It came down to Earth's magnetic field. When that field changes fast enough, it can push electrical current into long pieces of metal. That includes telegraph wires. But it also includes power lines, metal pipelines, railroad systems, and the large transformers that keep the grid running. The longer the conductor, the more current it can pick up. That is why a solar storm does not need to hit a building like lightning. It works in a much quieter way. The current can build slowly. Then it keeps flowing, not for a split second, but for minutes or even hours. That is what makes it so dangerous. Most electrical systems are built to handle normal power coming from generators and power plants. They are not designed for current being pushed into them by changes in the planet's magnetic field. And this current does not always look dramatic at first. There may be no flash, no explosion, no obvious warning. A transformer can simply start heating from the inside. Its metal core gets hotter and hotter, while the system around it struggles to understand what is happening. By the time the protection equipment reacts, the damage may already be done. That was the lesson hidden inside the telegraph failures of 1859. The storm was not just lighting up the sky. It was turning long metal networks on the ground into part of the electrical circuit. For a long time, scientists only had old reports to study. Newspaper stories, ship logs, personal diaries. Useful, yes, but not enough to answer the biggest question. How often does the sun do this? The answer did not come from a telescope. It came from ice and trees. Deep inside the Greenland ice sheet, scientists found thin layers that had unusual chemical signals. These layers were formed when high-energy particles from space hit Earth's atmosphere. Ancient trees kept a record too. When powerful solar particles reach the atmosphere, they can change the amount of carbon, 1,4 produced. That signal gets locked into tree rings as the tree grows. Years later, researchers found sudden carbon, 1,4 spikes in Japanese cedar and German oak. The dates matched. One major event happened around the year 774. Another appeared around 993. Both seem to have been stronger than the storm Carrington witnessed in 1859. That changes the story. The 1859 storm was not necessarily the biggest solar storm in human history. It was simply the first major one to hit after people had built a large communication network. That is why the damage became visible. A few centuries earlier, the sky might have glowed red and people would have written about it. But there were no long telegraph wires to catch fire, no power grid, no transformers, no satellites. The storm still happened. Civilization just had fewer systems for it to break. The ice and tree rings remind us that the sun has done this before. And some of those past events may have been much worse. On the 13th of March, 1989, the warning became real. A geomagnetic storm hit Earth. It was powerful, but still much weaker than the Carrington event. Even so, the power grid in Quebec collapsed in about 90 seconds. 6 million people suddenly lost electricity in the middle of the night. Outside, temperatures were around -30 degrees Celsius. The failure happened fast. The storm pushed unusual electrical current into the grid. Protective relays saw that current and treated it like a short circuit. So they did exactly what they were built to do. They disconnected parts of the system. Then the remaining grid became unstable. One section failed, then another, and the collapse spread almost instantly. The important part is this. The grid did not go down because the safety system was broken. It went down because the safety system worked correctly in a situation it had never been designed to handle. That is what makes the event so unsettling. The equipment followed its rules. The problem was that the storm created a threat outside those rules. Power was partially restored after about 9 hours, but the damage was not limited to Quebec. More than 1,000 kilometers away, a large transformer at the Salem nuclear power plant in New Jersey was physically damaged by the same storm. It never returned to service. It had to be replaced. And this was not a Carrington-level event. It was a smaller storm. Still, it took down an entire regional grid in less time than it takes to make a cup of coffee. The warning signs did not stop in 1859. They kept coming. Most people just never connected them. In May 1921, another powerful geomagnetic storm hit Earth. Signal stations in the United States, Sweden, and Japan caught fire. At the time, there was not much modern technology to damage. No satellites, no global internet, no massive power grid like the one we depend on today. So the event faded into history. Then came August 1972. A huge solar eruption crossed Earth's orbit even faster than the 1859 storm. But once again, Earth was not in the right place to take the hit. The storm still had an effect. Magnetic sea mines off the coast of Vietnam suddenly exploded. At first, the U.S. Navy thought enemy forces had triggered them. They had not. The sun had. Then, in 2003, a series of major solar storms hit around Halloween. Part of Sweden lost power. Airlines had to reroute flights away from polar regions because communication and navigation systems were at risk. Some satellites lost orientation. Astronauts aboard the International Space Station were told to move into a more protected section of the station. No global collapse followed. So, once again, the event was treated as a disruption instead of a warning. That is the pattern. 1,921 looked like an old telegraph problem. 1,972 looked like a strange military incident. 2003 looked like a temporary technology failure. Taken one at a time, each event seems manageable. Put them together, and the message is much harder to ignore. The sun has tested our systems before, and every time, we were either less dependent on technology or lucky enough to avoid the worst part of the storm. Then came the 23rd of July, 2012. The sun launched one of the most powerful eruptions ever measured. A massive cloud of plasma tore away from the sun at nearly 3,000 kilometers per second. It crossed the inner solar system in about 18 hours and 40 minutes. It passed through Earth's orbit, but Earth was not there. 9 days earlier, our planet had been sitting in that exact part of space. That is how close it was. The storm did hit something. It slammed into NASA's Stereo spacecraft, which was orbiting the sun ahead of Earth. The spacecraft survived, and the instruments captured clean data. For the first time, scientists had a direct measurement of a Carrington-level storm hitting a spacecraft. It just was not hitting us. The data showed that this eruption could have produced a geomagnetic storm as strong as, or possibly stronger than, the one in 1859. Had it happened about a week earlier, Earth could have taken a direct hit. The damage estimate mentioned in the video was around $2 trillion for the United States alone, and that was only the beginning. Recovery might not have taken days or weeks. It could have lasted years, especially if large transformers were destroyed and had to be rebuilt. Most people never heard about the event when it happened. There was no panic, no emergency broadcast. Daily life simply continued. But the danger had been real. We did not avoid that storm because our grid was ready. We did not stop it with better technology. Earth had simply moved out of the way. 9 days was not a shield. It was proof that modern civilization was still depending on timing, distance, and luck. The biggest weak point is not your phone. It is not the internet. It is the giant transformers that hold the power grid together. These machines are enormous. Some weigh several hundred tons. Many are as large as a small house. Their job is simple, but critical. They adjust voltage so electricity can move across long transmission lines and then reach homes, hospitals, factories, and businesses safely. The problem is what happens when one of them is damaged. A major transformer is not something a repair crew can fix in a few hours. If the internal core overheats and melts, the entire unit may have to be replaced. And replacements are not sitting in warehouses waiting to go. According to the scenario described in the video, a Carrington-level storm could overload around 300 large transformers at the same time. That is where the numbers become hard to ignore. Global production capacity is described as roughly 150 units per year, and each new transformer can take 12 to 18 months to build after the order is placed. These are custom machines. They are heavy, difficult to transport, and slow to install. So even if crews know exactly what failed, they may not have the equipment needed to bring the grid back online. That is why this kind of blackout could last much longer than people expect. Not a few hours, not a few days. In the worst-hit areas, recovery could take months or even years. The electricity may stop in seconds. Replacing the machines that carry it is the part that takes time. So, what actually happens when a modern city loses power for more than a few hours? At first, most people do not panic. On day one, the lights go out, and everyone assumes the power will be back soon. Phones still work because cell towers have backup batteries. People check the news, send messages, and wait. But those batteries do not last forever. By the end of the first day, parts of the cellular network begin to disappear. By day 3, the problem becomes much more serious. City water systems depend on electric pumps. Once those pumps stop, water pressure begins to fall. Taps may slow to a trickle or stop completely. Food in refrigerators starts to spoil. Hospitals switch to diesel generators and keep running, but now they are living on limited fuel. By day 7, that backup fuel starts running low. Intensive care units are under pressure. Ventilators, monitors, and other critical equipment cannot run without electricity. Telecommunication centers begin shutting down. Large data centers stay online with generators, but they burn through huge amounts of diesel. The fuel trucks may not arrive because gas stations and truck stops also need electricity to pump fuel. By day 14, grocery stores are empty. Most stores only carry a few days of inventory. Once deliveries stop, the shelves stay empty. Traffic lights are dead. Roads become harder to use. Payment systems stop working, so credit cards and digital banking become useless. At that point, people begin leaving the city, not because they want to, because the systems that made city life possible are no longer working. A blackout starts with darkness. But if it lasts long enough, the real crisis becomes water, food, medicine, fuel, and time. This would not be like a normal storm. After a hurricane, earthquake, or wildfire, help can come from outside the damaged area. Trucks bring food. Crews bring generators. Fuel, medical supplies, and replacement equipment can be moved in from cities that are still working. That is how recovery usually happens. But a major solar storm could hit several countries and continents at the same time. There may be no safe region nearby with enough power, fuel, or equipment to help. The factories that build replacement transformers could lose electricity too. Ports could shut down. Airports could stop operating normally. Fuel systems could fail because pumps, refineries, and distribution centers all depend on power. Roads and rail networks could become harder to use. So the problem would not simply be fixing the grid. The real problem would be fixing it while almost every system needed for the repair was also struggling. You need factories to build the equipment. You need electricity to run those factories. You need ports, trains, trucks, and fuel to move the equipment. And you need working communication systems to coordinate all of it. If those systems fail together, recovery slows down fast. That is what makes a powerful geomagnetic storm different from a regional disaster. There may be no outside waiting to come in and help. So how likely is this to happen again? One estimate mentioned in the video puts the chance of a Carrington-level storm hitting Earth at about 12% in any given decade. That does not mean it will happen on a certain date. It is not a countdown. It is a statistical estimate based on the storms we have already measured. But even as an estimate, 12% is not something you can casually ignore, especially when the damage could last for years. The good news is that this is not a problem with no solution. The grid can be made stronger. Better grounding can help control unwanted current. Special blocking devices can reduce the flow of geomagnetically induced electricity into transformers. Governments can build strategic reserves of critical transformers instead of waiting until hundreds are already damaged. The most vulnerable parts of the grid can be reinforced, and cities can prepare real plans for a long-term blackout, not just a few hours without power. None of that can stop the Sunday. That is not the goal. The goal is to keep one solar storm from turning into a much larger human disaster. In 1859, people did not understand what had happened. They saw the red sky. They watched telegraph machines spark and burn, but they did not have the science to connect it all. We do. We have the records. We have the spacecraft data. We have computer models, historical warnings, and real examples of grids already failing under smaller storms. The problem is no longer that we do not know. The problem is that we know, and we keep putting off the work. The sun will do this again. We cannot negotiate with it. We can only decide whether the next time comes as a surprise or as a threat we were finally ready to face.